Hi guys, we're going to go ahead and take a moment and summarize Chapter 26, which are the 3 chi-squared tests using a template. This template's going to be a bit different than the templates we've done in the past. Usually we do an interval and one test, interval outlined on the left side and the test outlined on the right, but there are no intervals for these 3 tests. And since the mechanics of these tests and the assumption conditions are really very similar, I thought we could just put them all on one. We're going to do the goodness of fit on the left-hand side, mostly. The hypotheses and the mechanics are very different. But assumption conditions and conclusion are going to say the same for both. I've also already typed up some of the information. Because you write the hypotheses in words, I thought I would just type them up for you. You can take a moment and look over those, but we've been really focusing on the null is really what distinguishes the 3 tests. I want to write a quick reminder up at the top of the page here that the goodness of fit are the one variable and one group tests. The other 2, homogeneity and independence, are going to be those two-way tables. Just ignore that if you can hear that. My phone's ringing at home. Homogeneity is the multi-group one, but it's still one variable, and the independence is the 2 variable. The reason why we're kind of linking them together is that they actually look like the same kind of data sets. They'll have a two-way chart with categories listed for both rows and columns. So the most challenging part is going to be to distinguish whether it's a homogeneity, where we're looking at multiple groups to see if they have the same distribution of that one variable, or is it an independence test where we have 2 variables and we're interested to see if they're independent or associated with each other. You really have to look at the context of the problem to figure that out. Alright, let's jump down to assumptions and conditions. There's a big giant set because whether it's goodness of fit, homogeneity, or independence, you're going to have the same 3 assumptions and conditions. And you just write 3 sentences. The first is that the data must be in count form. So we used to compare percentages with categorical data, but now we want to keep everything in counts. It's just the way the chi-squared mechanics work. The next is randomness of some sort. Usually it's a random sample, but you might have, for homogeneity, experimental data, and so then you might have random assignment to the groups. And then finally, it's a large enough check. You actually want to make sure it's the expected counts that you check must be greater than or equal to 5 for each cell. Expected counts are actually really important for chi-squared tests, and it's required that you write them down. So why don't you make yourself a little note, must write them down. So it's not good enough to just write expected counts are greater than 5 and put a check. You actually have to write them down and sort of give justification that, yep, I checked them and they are greater than or equal to 5. Also, at this point is usually when we name our test. So for some reason the chi-squared tests are named backwards. You say chi-squared test first, usually, and then you write the word for, and then whatever the name is. Goodness of fit, homogeneity, or independence. Again, the selection of the correct test is pretty crucial, especially with homogeneity and independence. So even though you might have the mechanics right, you might have the assumption conditions correct, your expected counts correct, you still would be describing the situation wrong, and therefore you would get points taken off because you haven't named the right test. So you want to think very carefully about that. Okay, so now let's look at the mechanics. The goodness of fit we're going to do on the left because that one you're going to do quite differently in your calculator. So for that, you're going to use your list. So why don't we write that at the top here? You're going to use your list. It's everything about these chi-squareds are different because we're used to making models and mean and standard deviations and statistics. It's just the whole process is very different. So for goodness of fit, in L1, you're going to put your observed counts. And that should be given to you. In L2, you're going to put your expected counts. And that you need to calculate. I'm not going to go and remind you again how to calculate them, but it's if they give you percentages, you have to figure out how many would be in each category. If it's uniform, you just have to evenly divide up the sample to get your expected counts. And then what you're going to do is in L3, you're going to type in parentheses L1 minus L2 parentheses squared divided by L2. And then the last step is to add up the L3 values to get your chi-squared score. Oh, and I said that was the last thing, but it's not. The other weird or different thing from a homogeneity test is the degrees of freedom. It's just your number of categories that you have minus 1. So goodness if it's a pretty lengthy process. L1's given. L2 you have to calculate, which hopefully you've done enough practice with that. L3 you have to calculate. And then you're going to add up all the values in L3 to get your chi-squared score. And then make sure you know what your degrees of freedom are. Okay, so let's now jump over to the homogeneity and independence. These are the super fast, easy ones. You're really going to want to lean on your matrices. What you're going to do is you're first going to, in matrix A, you're going to put in your observed table. Meaning the counts for the two-way table for that. And that will be given to you. Now matrix B is supposed to be your expected counts, but you don't actually have to type them in. Your expected counts will be done for you in matrix B when you perform the test. It's kind of a behind the scenes bonus that you get. But I can't not talk about the fact that you should know how to calculate an individual expected count. So I'm going to throw that on here for you. The formula to get a single expected count is equal to the row total for that particular category or cell, excuse me, times the column total for that particular cell divided by the table total. I sort of rushed through this last class, and I think it's an important thing that you have in your repertoire of formulas. I've seen a multiple choice question that just asks for a single one. So row total times column total divided by table total will give you each individual one. But if you need every single one of them, just go ahead and do it in matrix B. It does this formula for all of them like in an instant. And one more last thing, I'll kind of squeeze that in over here. How do you get your degrees of freedom for a two-way table? It is rows minus 1. Oh, I'm running out of room, sorry. Times columns minus 1. Okay, so the same exact thing happens for the homogeneity and independence in terms of mechanics. And we're actually still not done. There is a part of the mechanics that is the same for both of them, and that's what you actually have to write down. So I've already said you have to write down your expected counts, and I've already put degrees of freedom up in this box since they're different for each. You also have to write down degrees of freedom. But the final thing is you must write down the chi-squared formula. So don't just write chi-squared equals and like it comes up on the calculator. You want to write down the formula. Chi-squared equals the sum, parentheses, observed minus expected, parentheses squared, divided by the expected. That actually is on the formula sheet, so you don't have to memorize it. And that is our test statistic. So that's probably, our test statistic is one of the few things that we have had on every single hypothesis test we've ever done. It's just, this one's very strange. And then you're always going to have a p-value. Your p-value is going to be written like this for chi-squared, capital P parentheses, chi-squared is greater than, and then you'll just put in whatever that score is that you got above. But then actually getting the number, either they're going to give it to you, or you could always do a chi-squared CDF from your score, chi-squared score, comma, bunch of 9s, comma, degrees of freedom. No need to do this for homogeneity and independence because the test will do it right there for you. But you've got to write the correct notation. Alright, so that's a lot when it comes to mechanics. You want to take your time to really think about, do I need to use my list or my matrices? And these are the steps to what you need to do, but what you have to write down are, you definitely have to write down expected counts, degrees of freedom, the test statistic and the formula, and the p-value and the notation. And the last thing, I've already typed it in for you, is how do you write your conclusions? It's the same as always, the reject and fail to reject. But there's this new thing, we don't have any confidence intervals. So because of that, we want to actually extend our conclusions. If we reject, we want to say, what do we actually know about the differences between the observed and expected? So you want to just take a moment and look at what are the big differences. Only talk about the ones that are unusual. Don't talk about the ones that are close together. If you fail to reject, though, we don't have sufficient evidence that there's a difference or that they're associated, whatever the null is, so there's no need to do the component discussion. Alright, and that is your chi-squared template. Oh, one more thing. On the back, there are 3 examples of actual AP chi-squared tests, and of course there's one of each. So, you should take a moment and at the very least look over them and decide which one's which, and maybe use it to study for your quiz next class. All right.